Hello viewers, in today's session we are going to discuss another important and conceptual problem from integrals, and in this session we are going to evaluate this integral using the concept of differentiation under the sign of integration, right? So here we are going to make use of the famous Leibniz integral theorem, right? So let us first take this integral as I, right? So here we have this integral that is from 0 to infinity, and the integrand is e raised to minus x square plus alpha square over x square, and here alpha is a parameter, right? So in the concept of differentiating an integral under the sign of integration, what we do, we take this alpha as a variable, right? And we differentiate both sides with respect to this parameter, right? So in this case the parameter is alpha, so we'll differentiate this integral I with respect to alpha, and we'll take the partial derivative of this integrand with respect to alpha, right? So let us start. So here we'll write di over d alpha, and we'll take the partial derivative. So we'll write del over del alpha, and here we have 0 to infinity e raised to minus x square plus alpha square over x square, and dx. Now taking this operator del over del alpha inside the integral sign, so we have now 0 to infinity, and we write del over del alpha e raised to minus x square plus alpha square over x square. And when we differentiate this term with respect to alpha, then we take x as constant, right? So we have 0 to infinity, and the derivative of the exponential function e raised to minus x square plus alpha square over x square is given by the function itself. So here we have e raised to minus x square plus alpha square over x square, and then by chain rule we differentiate this term, that is a negative of x square plus alpha square over x square, right? And here we have dx. So now we can write 0 to infinity e raised to minus x square plus alpha square over x square. So we'll keep this term as such, and here we can now write a negative sign, and the derivative of x square with respect to alpha is 0, because here we are dealing with the partial derivatives, and x is taken as a constant. So we have simply minus del over del alpha, and here we have alpha square over x square, right? So now we can write 0 to infinity, and we have e raised to minus x square plus alpha square over x square, and here we have minus 1 over x square. So we can take 1 over x square outside this operator del over del alpha, because x is assumed to be a constant, right? And the derivative of alpha square with respect to alpha is 2 alpha. So here we have 2 alpha, and here we have dx. So now we'll proceed further with the help of method of substitution. So now let us take here this substitution, that is t is equal to alpha over x, right? So in order to proceed further, we'll make this substitution t is equal to alpha over x, so that dt over dx, now differentiating t with respect to x, we have now alpha, and here we have d by dx of 1 over x. So we have alpha d by dx of x raised to minus 1. So we have alpha, and the derivative of x raised to minus 1 with respect to x is minus 1 over x square. So here we have dt over dx equal to minus alpha over x square, and here we can see that we have alpha over x square, right? So now let us transform this integral in terms of t. So now let us change the limits accordingly. So here x varies from 0 to infinity. So when x is equal to 0, then here t is equal to alpha over 0. That is t tends to infinity. And when x is infinity, that is when x tends to infinity, then from this expression t tends to alpha over infinity, that is t tends to 0, right? So now we can write di over d alpha is equal to integral, and when x is equal to 0, then t tends to infinity. So here we have infinity, and when x tends to infinity, t tends to 0, and we have e raised to minus, here we have x square plus alpha square over x square. So from here we can now write x is equal to alpha over t. So here we have x square, so that is equal to alpha square over t square, and then here we have alpha square over x square. So t square is equal to alpha square over x square. So squaring both sides, alpha square over x square is equal to t square. So here we have t square, and then we have here minus 1 over x square 2 alpha. So we can write it as minus 2 alpha over x square dx, right? And here we have minus alpha over x square is equal to dt over dx. So we can now write dt is equal to minus alpha over x square dx. So here if we take this negative sign over here, then minus alpha over x square dx can be replaced by dt, and here we have the factor 2. So here we have 2 dt, right? So now we can write di over d alpha. So now we have here di over d alpha. We can take this 2 outside this integral notation. So we have 2 here, and we can here interchange the limits. So we have 0 to infinity, and we put a negative sign over here, because from the properties of definite integrals we know that a to b f of say t dt is equal to negative of b to a and f of t and dt. So when we interchange the limits, then we have a negative sign over here. So we have here interchanging the limits, we have a negative sign, and then we have e raised to minus, we can take here a t square, then we can write alpha square over t square, and here we have dt, right? So now let us look at this integral. Now see, the original integral is 0 to infinity e raised to minus x square plus alpha square over x square dx. So this integral is same as this integral except the variable, right? So from the dummy variable property of definite integrals, that is if we have a to b f of t dt, then the value of this integral is same as a to b and f of say here we take the variable y, dy, right? So if we change the variable, then the value of the definite integrals, it doesn't change, right? So here this integral can be taken as I, because here the variable is x and here the variable is t, right? So from this property of definite integrals, where we change the variable and the value of the definite integral remains the same, so we have here minus 2 times I, right? So we have di over d alpha is equal to minus 2I. So this is a first order and first degree differential equation, and now we have to solve this differential equation, which is of the form that is variable separable form. So here we can here separate the variables. We can now write di over I is equal to minus 2 d alpha. So separating the variables I and alpha. So now integrating both sides, we have di over I is equal to minus 2. Here we have d alpha, and c is the constant of integration. So now the integral di over I is natural log of I, because we know that integral dx over x is equal to natural log of x. And here we have minus 2 alpha, and c is the constant of integration, right? So now we have this equation, and now our aim is to get the value of this constant of integration c using some condition, right? So let us now again look at this integral. So here this integral I is taken as a function of alpha. That is, we can write this integral as I is equal to I alpha, and we have 0 to infinity and e raised to minus x square plus alpha square over x square, and here we have dx. So now if we take alpha is equal to 0, then let us see what happens here. So we have I is equal to I of 0, and here we have 0 to infinity, and we have e raised to minus x square plus 0, because alpha is equal to 0. So we have e raised to minus x square and dx, right? So now this is a standard integral that is also known as the Gaussian integral, and the value of this integral is equal to square root of pi over 2. So here we'll make use of the direct result. The value of the integral 0 to infinity e raised to minus x square dx is equal to square root of pi over 2, right? So when we take alpha is equal to 0, then the value of the integral I is equal to root pi over 2. So now we have this condition, that is, when alpha is equal to 0, then I is equal to root pi over 2. So let us make use of this condition to get the value of c. So taking these values in this equation, we have natural log of root pi over 2. I is root pi over 2. Here we have minus 2 times 0. That is, here we have minus 2 times 0, because alpha is 0, and plus c, that is simply equal to c. So the value of constant of integration c is equal to natural log of pi over 2, right? So let us substitute this value in this equation. So we have a natural log of I is equal to minus 2 alpha plus natural log of root pi over 2. So now taking this term to this side, we have natural log of I minus natural log of root pi over 2 is equal to minus 2 alpha. Now using the properties of logarithms, that is natural log of a minus natural log of b is equal to natural log of a over b. So here we can now write natural log of I over root pi over 2, and here we have minus 2 alpha. So we can now write natural log. We can take this 2 to the numerator. So we have 2i over root pi, and here we have minus 2 alpha, right? So here we can now write this natural log as log of 2i over root pi to the base e, right? And here we have minus 2 alpha. So now from this equation we can write e raised to minus 2 alpha. E raised to minus 2 alpha is equal to 2i over root pi, right? So here we have used this result, that is log b to the base a is equal to c, then a raised to c is equal to b. So now we have I is equal to, that is 2i is equal to root pi times e raised to minus 2 alpha. So I is equal to root pi over 2, and here we have e raised to minus 2 alpha, right? So the value of this integral is equal to square root of pi over 2 times e raised to minus 2 alpha. So this is the value of this integral using the concept of differentiation under the integral sign.